All right, let's look at how we can calculate this wavelength here. It comes out to 486.1 nanometers. That would be the wavelength of the light released when the electron falls back from a transition of n equals 4 down to n equals 2. Alright, so here is an example of the same sort of question. And we're going to split it up into three parts. First of all, we're going to find the energy of the photon uh, due to that transition. Then we're going to find the frequency, and then we'll find the wavelength. And it's all from the movement of an energy of electron from energy level n equals 4 down to n equals 2. So the energy can be measured using this formula here, which is the energy for the electron falling from a transition of n equals 4 to n equals 2. And what we do is we make the n2 the larger one, 4, and make the n1 the smaller one, 2. This will give us an energy that has a positive value because we're going to be subtracting a small number from a larger number if we do it this way. If you accidentally put the 4 here and the 2 here, or you reverse them, you'll end up with a value that is the same, but it will be negative. And that's okay, because what you're saying then is that the energy is being released, and that's fine. But if you do that, you'll have to be careful because you don't want to be putting a negative energy in here and ending up with a negative frequency, which is going to be impossible. So I think it's just safer to go with the smaller value here first and then the larger value here, and that will make sure that you end up getting a positive value for your energy. Alright, so you can get the energy from doing that. This will end up being 1 over 4 minus 1 over 16. And since we want the energy in kilojoules, that's why I've done this conversion here, times 1 kilojoule over 1,000 joules. And that gives us our energy, 4.086 times 10 to the negative 22 kilojoules. Next, we can figure out what the frequency of that light is, and we can do that using the formula that we saw earlier, which is E equals h nu, where h is Planck's constant, and nu is the frequency, and E is the energy. We use the energy that we calculated up here, but that energy has to be in joules. So what I've done is I've done a conversion from kilojoules to joules, which is times 1,000 joules over 1 kilojoule. And that gives me my energy here, 4.086 times 10 to the negative 19 joules. Not this one here, 4.086 times 10 to the negative 19 joules. And we're dividing that by Planck's constant, which has the value of 6.626 times 10 to the negative 34 joules seconds. What that gives us is a frequency that has the unit 6.166 times 10 to the negative times 6.166 times 10 to the 14 hertz, or if you'd like, seconds to the minus 1. So that still works out as far as the units go, or seconds to the minus 1, or if you like, slash seconds. So the seconds are on the bottom here, so that still works out okay. Once we've got that, we can then go ahead and calculate the wavelength. Now we're going to use the formula C equals nu lambda, where C is the speed of light, nu is the frequency, and lambda is the wavelength. So if we rearrange that, we'll get lambda equals C over nu. So that's 2.998 times 10 to the 8th meters per second. That's the value given for the speed of light. And then we've got the frequency here, which we calculated up here. And what I've done is I've converted that to seconds to the minus 1, which is the same as hertz. And what you'll see there is that would give us a value of lambda in meters. Now what we're after in the problem is a value in nanometers. Now the conversion from nanometers to meters is that 1 nanometer is 10 to the negative 9 meters. The reason we use nanometers is because we get values that are usable. If we just leave it in meters, we'll get a very small value which doesn't have a great deal of meaning to us, but if we convert it to nanometers, we'll get something in the hundreds or thousands, which looks a lot nicer. So we'll multiply that by 1 nanometer over 10 to the negative 9 meters. You can see how all the units cancel, and we'll be left with nanometers at the end. So that's how we get our value of 486.2 nanometers, which is very comparable to what we saw on the website here, which stated that we've got 486.1 nanometers for the transition going from n equals 4 down to n equals 2. Alright, so just summarizing what I did as far as the calculations go. The first calculation was to calculate the energy based on the given Bohr transitions, which was from n equals 4 to n equals 2. We'll use the smaller value here versus the larger value for the n equals 2 to the n equals 4, and that will ensure that we end up getting a positive value for our energy. We then calculated the frequency by using E over the energy calculated here over the Planck's constant, the energy being in joules, not kilojoules for this step, which gives us a frequency value in hertz or seconds to the minus 1. Then we can calculate the frequency, the wavelength using the speed of light over the frequency. Frequency comes from up here, and the wavelength also gets converted into nanometers along the way, and we end up with our nanometer value down here.